11.2 notes with you. Specifically, I wanted to talk about the z-star values that you were taking a look at. Specifically, these values were 1.645, 1.96, and then 2.57. If you don't recall those, please go ahead and pause the video and grab those notes to have out in front of you. Okay, so let's go ahead and talk about this. Now, these values that you're taking a look at for under z-star, these are referring to certain confidence levels, or they are used to help you create confidence intervals with a certain level of confidence. So if you want to create a confidence interval that you are 90% confident that the true population proportion or population mean, again depending on the problem that you were taking a look at, exists, this would apply to a confidence level that is 90%. If you are working with 1.96, and odds are with a lot of the problems that you will be taking a look at, they will apply to a confidence level of 95%. And then if you want to construct a confidence level where you are 99% sure that the confidence level, or that the population proportion or population mean exists in there, then that is going to be, you would use the 2.57 in this case. So what I want to go ahead and do, and what I've already done in class with you, is kind of describe to you where these values are coming from. We can actually use prior knowledge in order to actually figure out where these values are. So one of the first things that I'm going to do is we're going to do a little bit of background. Recall from previous lessons, we have worked with a normal distribution, so that unimodal symmetric distribution that you have been looking at probably since maybe chapter 1 is coming back again. And what I'm going to do is, specifically, I'm going to work with the standard normal distribution. And why the standard normal? Well, first off, recall that the standard normal has a mean or a center at 0. And then it has a standard deviation of 1, which allows me to quickly create the distribution number line underneath it. Okay. Recall that we use the standard normal distribution when we work with z-values. So the z-star value that you are working with actually is connected to the standard normal distribution. Okay. They go hand in hand. The z-values exist in the standard normal distribution. Okay, so if you also recall, we had worked with the 68, 95, 99.7, and yep, I'm a little bit off on my drawing here, so I apologize, but recall that 68% of your values are one standard deviation away from the mean, and then if we go 2 standard deviations out, then we know that 95% of the data is held between the 2 standard deviations away from the mean. And lastly, if we were to go the full 3, we would say that this is 99.7%. Now, please note that these values that we are taking a look at here, the 68, 95, and 99.7, these are estimates. Okay, we're kind of working with values that are not quite 68, 95, and 99.7%. These are just estimates that we have been working with. So now that we're starting to construct confidence intervals, we want to be as specific and as accurate as possible. So we need to step away from these estimates, and we actually need to work with the actual values here. So I'm going to repeat what we had done in class with respect to the 95% confidence interval. So if we were to go ahead and, again, take a look at a standard normal distribution, so a mean centered at 0, and then a standard deviation of 1, so here we go. We are interested to find out, okay, if we're 95% confident, we want to basically create, again, we'll use our old information here. We want to know in this particular instance, what this value is right here on your number line. Okay? And if you recall from class, it's not quite at 2, but it is close. So that's why I have that purple line close to 2. So in order to actually figure out what this actual value is here, we can use the inverse norm function on your calculator. And in order to do that, remember that the inverse norm calculation reads everything from all the way to the very extreme left up to our stopping point. So what we really want to note here is that from our stopping point all the way to the extreme left, this is 97.5%. So to get very specific, so from here to our stopping point, here's our 95%, and let's see if I can do that in black and have it appear a little bit better. And then we also need to take into account this percentage. Well, this percentage here would be 2.5%. Recall that underneath the entire curve, we have 100% of our probabilities. If we've taken into account the center 95%, then on either side of the distribution, we should have 2.5%. So that's where we're getting these values. So the 97.5% is the 2.5% plus the 95%. So when we put this into our inverse norm function, remember that this is the percentile that goes in the first value. So there's our point 97. Sorry about that. 97.5. Remember, we want to write our value as a decimal. Our mean is 0, and our standard deviation is 1. If you go ahead and put that into the calculator, you'll get the following value. We get 1.959963986. Ideally, you would want to work with this value. I mean, that would give you the most accurate representation when constructing a 95% confidence interval. But we're going to go ahead and simplify this down and say, okay, this is about 1.96. And again, note that I'm rounding to the second decimal place. I look to the number on the right, and since it is bigger than 5, I need to round this 5 up. Okay, so this is how we got 1.96 for a 95% confidence level. Let's repeat the same process. Let's go ahead and take a look at it for a 90% confidence level. Again, we'll start off with our standard normal distribution. And if I'm interested in a 90% confidence level, I'm totally going to try and, well, we're going to kind of make this up as we go along. Let's say that, well, we know from here, from one standard deviation, that's about 68. And we know if we go 2 standard deviations, it's about 95. So let's say we're somewhere in here for 90%. Okay? So this is our 90. And we know that our stopping point in this case is somewhere around here. Okay. Recall then that we will go ahead and we will use the inverse norm here. And our percentile has to go all the way from the extreme left up to our stopping point. Okay. So if we know that this shaded area here is our 90% confidence area, or our range, we still need to take into account this shaded area when working with the inverse norm function in the calculator. So if this center is 90%, this piece must be 5%, and this piece must be 5%. Again, if we add up all 3 pieces, we get the 100% probability underneath the curve. So our percentile in this case will be the 90 plus 5%, or 0.95. Our mean is 0, and our standard deviation is 1. If you were to go ahead and calculate this, we get the following solution. We get 1.644853626. Okay? So in this situation, again, if we rounded this to maybe the third decimal place, so if we round it here, we would go ahead and take a look at the number on the right. So this simplifies to about 1.645, which is the same value that we have noted above. Okay. We can repeat, again, the same thing for a 99% confidence level. So again, here we go. You're going to get very familiar with standard normal distributions. Okay, so if we were to go ahead and do this, so we know that 99.7% happens somewhere 3 standard deviations away. So I'm just going to scoot this in a little bit and assume that from here I have about 99% in between those two marks. But again, if we're doing the inverse norm, it reads from the stopping point all the way to the extreme left. So I have to take into account this little bitty piece on the left side. Well, that must be 0.5% over here, and because this is symmetric, so in other words balanced, there should be another 0.5% here. Again, if we add up all 3 of those values, it should total out to 100% underneath the curve. So again, if we were to calculate this, this would actually be 0.995 when we add these two values together, a mean of 0 and a standard deviation of 1. And we get the value 2.575829303. So I believe our value, we actually have a small rounding error on our notes, so we would actually want to round up. But I believe if you also read your textbook, we would say, if we rounded this to the third decimal place, say, then this would be 2.576. Okay? So, there you go. This is how we use these values. To give you a little bit more of a background here, we can basically tell you what these numbers mean. These numbers that you're working with, let me scoot back up for you to the very top. So these numbers that you are seeing, these almost are acting like the magnitude for your standard deviation. In words, they're telling you basically to multiply your standard deviation value by that number. So for example, if you want a 95% confidence interval, you are basically almost, but not quite, doubling the size of your standard deviation. So this is basically, the z-scores that you're working with are telling you how far your confidence interval should expand out from the mean. So very similar to the question that you had received on your previous exam. What does a z-score tell you? Well, it tells you how far away from the mean you are going. It's impacting your standard deviation. Since we don't work with standard normal, or since not every single distribution that we work with has a standard normal distribution, these z-scores help you to adjust your standard deviation for your particular problem. Okay, so I hope that that was helpful. If you do have any other questions, please let me know, and let me know if this video was helpful. Thank you.